Ever rubbed a balloon on your head and watched your hair go full Einstein mode? That wild hair moment isn't just static, it's electric. Now, take that idea and stretch it to a pair of charges. One positive, one negative, and there you have it. That's how we arrive at the concept of electric dipoles. An electric dipole is a pair of equal and opposite charges like plus Q and minus Q separated by a fixed small distance. The strength of this configuration is called the dipole moment. Here's how we define it. Dipole moment equals the magnitude of charge multiplied by the separation between the charges. So, in words, P equals Q times 2A, where 2A is the total distance between the charges. The direction of the dipole moment is from the negative charge to the positive charge. Think of it like an arrow pointing from minus to plus. Why should we care? Because dipoles are everywhere. Water molecules, they're dipoles. Proteins in your body, full of them. Even your microwave heats food by targeting dipoles. They shape chemistry, biology, and even weather. Let's see what kind of electric field a dipole creates. In part A figure, we're looking at a point along the axial line. That's the straight line passing through both charges. Electric field on the axial line equals 1 divided by 4 pi epsilon naught, multiplied by 2 times the dipole moment, divided by the cube of the distance from the dipole's center. So, the farther you go, the weaker the field becomes very quickly. Now look at part B, the equatorial line. This is the line that cuts the dipole perpendicularly through its center. In this case, the electric fields due to the two charges oppose each other. The resulting field is weaker, and its direction is opposite to the dipole moment. Electric field on the equatorial line equals 1 divided by 4 pi epsilon naught, multiplied by the dipole moment, divided by the cube of the distance from the center. Water molecules are natural dipoles. The oxygen atom pulls electrons more strongly, making that side slightly negative, and the hydrogen side slightly positive. This is why water sticks to surfaces and dissolves salts so well. Dipoles literally make water the universal solvent. To wrap it all up, an electric dipole consists of two equal and opposite charges held a small distance apart. The strength of this configuration is captured by the dipole moment, which points from negative to positive charge. The electric field it creates depends on where you observe it, stronger and aligned with the dipole moment on the axial line, and weaker and opposite on the equatorial line. We saw this clearly both mathematically through field equations and visually in the diagrams.